Hi, today I want to talk about the difference between shock and electrocution. I often hear people talk about them almost interchangeably and it kind of annoys me. So let's go into what the differences are and yeah, I can't draw. Sorry. So you may have heard before that it's not the voltage that kills you, it's the current. Well, that's true. So why are there signs that say danger, high voltage? Well, there's a reason for that. And it can be explained very simply just by using plain old Ohm's law. You can see that the current in amps equals the voltage divided by the resistance. In this case, the resistance is your skin resistance. So even if you say that the resistance of your skin stays the same, as the voltage goes up, because it's in the numerator of the equation there, as the voltage goes up, the current also goes up. So the higher the voltage, more dangerous it is. Although, as we'll see, that's not entirely true. Okay, so when I talk about fatal currents or currents that will shock you, what am I talking about? What kind of magnitude are we talking about? Well, I've made a little chart here, and sorry, my handwriting is maybe worse than my drawing abilities, but we're talking in the order of milliamps. Yeah, if you think about it, what are the circuit breakers in your house? 15, 20 amps are typical. Way larger, orders of magnitude larger than the milliamps we're talking about here that can severely injure or kill you. So anyhow, I made a little chart here, and when you're talking about anywhere from 0 to 10 milliamps, you're going to have a bit of a tingling sensation, and probably if you've been into electronics or electrical things, you've probably been in this realm before where you touch something and got a little bit of a tingle, a little bit of a zap. As we move up here, anywhere from 10 to 100 milliamps, say 50 milliamps, somewhere in there, you're going to have pain and breathlessness. We're talking about a much more severe shock here. A shock like this feels like somebody just kicked you in the chest. Maybe some of you have had this kind of shock. I sure hope not. But, that's the next level. By the way, when I'm talking about shocks here, I'm talking about across your heart. This is current going directly across your heart. So on our little dummy man here that's getting shocked, we're referring to from your left hand down to your left foot. Why your left hand? Well, if you look at the human body, my heart's roughly in this area here, so it would be the current going through my left arm, down through my heart. That would be an issue. It would be less of an issue here on my right hand and down my right side, as it doesn't go directly through my heart. The worst case scenario is actually from hand to hand, and for electricians that's very dangerous because they're often working with both hands. That's why they tell you when you're doing electrical work, put one of your hands behind your back. It lessens the risk that you're going to get a fatal shock. Although if I could give any advice based on what I just told you, keep your left hand behind your back. Sorry, lefties. Anyway, moving up. Now we're getting into the 100 to 200 milliamp range. This is when you have to worry about something called ventricular fibrillation. Medical term, obviously. What does that mean? Well, it doesn't necessarily mean death, but it means that your heart is having random contractions. It's not allowing the blood flow in a normal way. What does this do? Well, this makes the tissues start to die, unfortunately, very slowly. The bigger issue is it's not pumping blood, it's not getting blood to your brain, and eventually it will stop your heart. So if somebody goes into ventricular fibrillation, you need to give them breathing, you need to give them chest compressions to try to bring them back. Chances, if you're in that 100 to 200 milliamp range of bringing somebody back, I hate to say, is relatively low. Although, as we go up in current here, from say 200 milliamps and up, maybe say 500 milliamps or even more than that, maybe okay. What? Wouldn't it make sense that as you go higher in current across your heart that it gets more dangerous? Well, normally yes. But the issue is this ventricular fibrillation. What's happening is as this current gets more intense, it actually gets to a point where your heart just clamps. And it's not the pulsing of your heart that you have to worry about anymore. Yeah, your heart will or could potentially stop, But it's been found through studies that you can actually have a better chance of restarting the heart with chest compressions and breathing, because there's not as much damage done to the actual heart itself. Although, as you get up into these high current levels, you're more prone to burns. You could have more tissue damage, could have brain damage. Any of your soft tissues are at risk. And in fact, I've even seen videos, and this is a bit gruesome. If you're afraid to hear it, then fast forward a little bit. But I've seen a safety video where there was an electrician working on a panel. His arm is like this. There's a metal plate behind him, and with his arm at a right angle, he accidentally touches a live circuit. It goes through his arm, comes out of his arm at a right angle, goes into that metal plate, and it actually blows his forearm off. So it can be very dangerous for other reasons when you talk about these high currents. But it's the 100 to 200 milliamp region that you have to worry about electrocution. Electrocution is a type of death. Shock is something that happens to you. You can be electrocuted because of a shock, but electrocution itself isn't a shock. So if you touch something and it zaps you, you don't say, I was electrocuted by it. If you were electrocuted, you're not alive to tell the story. You say that you were shocked by it, or zapped, or you got a jolt. But electrocution specifically is a type of death. Much like if you were to say, I drown. Well, no, maybe you almost drown, or maybe you drowned and somebody brought you back, I suppose, but drowning is also a type of death. Aspiration is what you would say, or choking is what you would say if you got fluid in your lungs, but you survived it. So anyhow, I thought it might be interesting to go a little bit further than this and actually test the resistance of my own skin and see what kind of voltage it would take to give me a lethal shock in the current conditions. It's early spring, it's relatively dry. My skin's pretty dry right now. We'll try wetting it and see what difference that makes. We'll try a few different scenarios and see what kind of voltage it would take to make that a lethal scenario. Okay, so I'm going to use my Fluke 87 today because, well, why not? And just for fun, I want to find out how much voltage it would take to kill me. For fun, right, yeah. Anyhow, I'm just going to grab these leads here. My hands are fairly dry. I'll use maybe like a medium pressure here. I can grab it kind of tighter and get that voltage, or that resistance to go down, but let's just call it, say, about 2 meg. So let's figure out what the minimum amount of current it would take to necessarily kill me. So 2 meg, that's 2 times 10 to the 6. So it's current times, or I'm sorry, resistance times current, which is 0.1. And that would take, what is that, 200,000 volts. That's pretty high. That's relatively high. So my chances are pretty good that I wouldn't get electrocuted that easily. Okay, now I'm going to do the same thing, but I'm going to lick my fingers. And if you watch my other videos, you know I kind of have a propensity for doing so. So I'm just going to lick my fingers, and I'm going to grab these again and see how that changes. So now we're looking at, say, it changes a lot. Let me just check this. Yeah, it's just changes with pressure, how wet your fingers are. I'm going to say the lowest is about 700K. So let's go with 700 times 10 to the third. That's a resistance times 0.1 amps. So with wet skin, it would only take about 70,000 volts to kill me. Now, one thing I'll point out, because you're noticing that these numbers are relatively high, you're probably thinking, well, people have died at 120 volts. That's true. That's because your skin has a very high resistance, even when wet. What normally creates the issue is that when the skin gets punctured, as is easily done with wires, or when you get zapped, you tend to grab onto things because of muscle contractions, and that will tend to pierce your skin. Even high voltage itself can actually pierce the skin and get to the lower resistance inner part of your body. and that's what actually creates the issue and causes it more likely to be shocked, or electrocuted, I should say. Because you're getting shocked, the worry is electrocution. Okay, so I've put one lead in the ground terminal. That's earth ground in the middle there in the green. That's the earth ground connection on that power supply there. What I'm going to do is I'm going to grab the other connection. Sorry, that's blurry. I'm going to grab the other one, and we will see with, show you my feet here, with shoes on. These are Converse Chucks, if anybody's interested, on a tile floor that is actually a concrete slab that is grounded. So what we're going to do is we're going to see what my resistance to ground is through this concrete floor with shoes on. So I'm going to wet my finger just to give it a better chance here, and I'll bring my calculator in. And let's see what we get. Nothing. So the rubber on the bottom of my shoes gives me a good enough of resistance to ground to protect me. That's good. Okay, so I'm now barefoot and I've gone handheld here, and I just want to show you that the Penguin says that it's about 60 degrees down here. I don't know if you can see it, it's pretty dark, but it's about 60 degrees Fahrenheit down here on a concrete slab. So yeah, my feet are quite cold. But what I'm going to do, let me set up the camera here on the tripod, get it focused on the ground, and I'll be right back. Okay, I've actually gotten water that I use for the sponge on my solder station, and I'm going to pour it on the tile here, just a little bit. I don't want to make a huge mess. Shouldn't take a lot. And I want to point out, do not do what I'm about to do unless you really know what you're doing. Okay, so I'm going to stand in this. Oh, that's very cold. For science, right? Probably some of you wish I would take an actual shock for science. Sorry, not going to happen today. Okay, so I'm standing in water on a grounded concrete floor. I'm going to wet my finger here and grab the other lead. Wow, you know, I'm kind of surprised. You know, I know this is a grounded floor. It could be the tile there is enough to protect me from the actual shock, but the resistance of this circuit is actually higher than my meter can measure, which is a good thing. That means I'm relatively safe here. So yeah, sorry, couldn't do anything to kill myself today, but yeah, I'm apologizing for that. But I was hoping I'd get some kind of reading. That would have been interesting. Yeah, perhaps I need to get bare concrete. I'm looking around. I don't see any in this room. I don't know of any bare concrete around here. Maybe we'll have to try it again some other time. But there you go. Just wanted to kind of explain the difference between shock and electrocution. Obviously, shock is, you know, when you feel a jolt, and electrocution is a type of death from shock. Anyhow, I hope the safety tips in this were useful to you. Please, please stay safe. Whatever you do, whether you're an electrician or you do low voltage electrical work, just always try to be safe and think before you do anything. Okay, well, hope you found that interesting. Make sure that you subscribe if you haven't already done so. Make sure you like the video, thumbs up, and follow me on Twitter at OhmsAtHome. Thanks, we'll see you.